morning, one and all. Myself, Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal, Hyderabad. So, in the today's lecture, we are going to learn electromagnetic wave characteristics. Introduction to electromagnetic wave characteristics, then followed by how the wave is propagating in different media like free space, conducting, and dielectric media. Then we are going to learn the wave equation or electromagnetic wave equation, also called as uniform plane wave equation. Right? So before going to derive the mathematical equation for the electromagnetic wave, then let me introduce first what do you mean by wave, then what are the different examples for the waves, then how the uniform plane wave is to be defined. Then from that we are going to derive the equation for electromagnetic wave equation, also called as uniform plane wave equation. Right? So before going to discuss about the waves and all, let me introduce first of all what are the topics which we are going to learn in this particular module called electromagnetic wave characteristics. So firstly, wave equations for the media means for free space media or conducting media or dielectric media. Then uniform plane waves definition. Then how those uniform plane waves are to be formed. Then we can learn relations between electric field intensity and magnetic field intensity gives us electromagnetic wave equation. Then how the wave is uniform plane wave or electromagnetic wave is propagating in lossless media. Then we are going to learn electromagnetic wave propagation in good conducting medium. Then electromagnetic wave propagation in good dielectric medium, followed by polarization. What do you mean by polarization? Different types of polarizations. Now we are going to learn in this particular module. So firstly, what do you mean by wave? What are waves? What carries the wave? Then different examples for the waves. So according to the definition here, a disturbance that transfers energy from one place to the another place is simply called as a wave or a signal. So definition of a wave. So a disturbance that transfers energy from one place to the another place is called as simply a wave. And what carries the wave? So a medium means the wave carries a medium. Means what do you mean by a medium? Means a medium is the material through which the wave can be traveled. Okay? A medium can be a gas or liquid or a solid. And one important point we need to remember is here is not all the waves requires a medium to travel. Means in order to send the or in order to transfer the energy from one place to the another place need not consider every time, means need not require every time a medium. Right? So not all the waves requires a medium to travel. Then light from the sun travels through empty space, where empty space is an example for free space medium. And here is an example in general. We'll consider an analog wave is an example. Looks like here tides or the general waves, an example for the waves. Now, another words we can define, waves are means of transporting energy or information from one place to the another place. Or in the technical way, we can define the wave is a function of both space and the time. Means in general, uniform plane wave can be expressed as like E of x comma y comma z and h of x comma y comma z. Along with all these three parameters, it is also varies with independent variable called t along here also t. So if we combine E and H, then the wave is said to be here uniform plane wave or electromagnetic wave. So a wave is a function of both space and the time. And some of the examples for the waves are radio waves, TV signals, radar beams, and light rays. These are the different examples for the wave. Then, what are the different characteristics of the different media? How the electromagnetic wave is propagating in different media, then depending upon the different characteristics of the wave. So first consider free space medium, and the notations are for the free space medium are given by sigma equal to 0 and epsilon equal to epsilon naught and mu equal to mu naught. So generally we can define the wave characteristics means with respect to the conductivity and with respect to the permittivity and with respect to the permeability. These are the general characteristics of the wave in order to move or in order to propagate one place to the another place. These are the three important characteristics we need to follow for each and every media. Hence, for the first medium is called as free space medium. In that, the representations for the three characteristic wave parameters are for the conductivity ideal value of the free space medium, it will be equal to 0 and epsilon is replaced by epsilon naught and mu is replaced by mu naught. So in general, the formulas for epsilon and mu are given by here. Epsilon equal to epsilon naught into epsilon r and mu is mu naught into mu r. For a free space medium, this epsilon r, nothing but relative permittivity of the material, is replaced by here 1 for the free space. Similarly, relative permeability of the material is replaced by 1 for the free space medium. Hence, these two are considered as epsilon equal to epsilon naught and mu is given by mu naught. And by default, we know that epsilon naught and mu naught values are given by epsilon naught is 8.854 into 10 power minus 12 farad per meter and mu naught is given by 4 pi into 10 power minus 7 Henry per meter. Right? So in order to define or in order to analyze the wave which is traveling or which is propagating in free space medium means these are all the important characteristics we need to remember. So for a free space medium, conductivity equal to 0 and permittivity of the free space medium is replaced by epsilon as epsilon naught and permeability is mu naught is replaced by mu naught. Why? Because for a free space medium, epsilon r and mu r is equal to 1. Next, second medium is considered as lossless dielectric medium. As we know that depending upon the electrical properties of the materials, generally the materials are broadly classified into three types. Conductors, first case as conductors, second case as semiconductors, and third one is insulators. So here conductors are also called as metals. All the metals are examples for conductors and all the insulating materials are also called as dielectric materials. Right? So for the conductor's case, ideal value of the conductivity is equal to infinity. For the insulator or dielectric material, ideal value is equal to 0. For a semiconductor's case, the conductivity which lies between the range of insulators and the conductors. So for a lossless dielectrics, name itself tells us that dielectric medium, ideal value of that conductivity is equal to 0. Lossless defines no loss in the signal. So lossless dielectrics characteristics are given by here sigma equal to 0 and epsilon is replaced by epsilon naught and epsilon r and mu is given by mu naught into mu r, or the condition which we need to satisfy for the lossless dielectric medium is sigma is far lesser than that of the omega epsilon. Means when we compare with the signal frequency with the conductivity, at very low conductivity case, at high frequencies case, medium behaves as dielectric medium. So in order to act as lossless dielectric medium, it must obey the condition that sigma is far lesser than that of the omega epsilon. Next, third case is lossy dielectric medium. Name itself defines that or determines there must be some loss in that particular signal. Hence, the sigma value which is to be considered as sigma is not equal to 0. And epsilon is given by epsilon naught into epsilon, and mu is given by mu naught into mu r. Similarly, the fourth case we are going to consider is good conductors. For the good conductors, the conductivity value which is approximately equal to infinite, and epsilon is replaced by epsilon naught, and mu is mu naught and mu r. The condition which we are going to consider for the good conducting medium is sigma is far greater than that of the omega epsilon. So, based upon this condition, we can say that at very high conductivity case, at low frequencies case, medium behaves as dielectric medium, right? So, these are the two different wave propagations we are going to consider in general as lossless dielectrics and good conductors, where lossless dielectrics is also called as perfect dielectrics and good conductors. So here, in order to work it as a lossless dielectric medium, it must satisfy the condition is sigma is far lesser than that of the omega epsilon, and for the good conducting medium, the condition which is to be satisfied is sigma is far greater than that of the omega epsilon, right? So in order to analyze all the wave characteristics, the propagation of the wave characteristics in different media like free space, lossless dielectrics, lossy dielectrics, and good conducting medium case, it has to consider the wave motion or the propagation of the wave as to be depending upon all these conditions, right? So for the free space medium, sigma equal to 0, epsilon is equal to epsilon naught, and mu equal to mu naught. For a lossless dielectrics, sigma equal to 0, epsilon equal to epsilon naught into epsilon r, and mu is mu naught into mu r, and the condition it has to obey is sigma is far lesser than that of the omega epsilon, or we can consider it as sigma by omega epsilon is far lesser than that of the 1, right? So either of the conditions it has to satisfy, then only it acts like a lossless dielectrics. And the third condition is lossy dielectrics. As the name itself resembles that, lossy defines there must be some loss in the signal. That the case, the sigma value which is not exactly equal to 0, hence it is sigma naught is equal to 0, and epsilon and mu can be defined respectively as epsilon naught epsilon r and mu naught mu r. Next, for the fourth case, good conducting medium case, sigma is to be ideally equal to infinite, and epsilon equal to epsilon naught into epsilon r. Mu is nothing but mu naught into mu r, and the condition it has to satisfy is sigma is far greater than that of the omega epsilon, or sigma by omega epsilon is far greater than that of the 1. So based upon these two conditions, we can say that at very low conductivity, sigma is low and omega is high, medium behaves as good dielectric medium. And if sigma is high and omega is low, means at low frequencies, medium behaves as good conducting medium. We need to remember these two important points. Okay, so a waves are means of transporting energy or information from one place to the another place, and technically we can define a wave is a function of both space as well as the time. Okay, so then we have seen some of the examples or how the wave is propagating in different media like free space, lossless dielectrics, lossy dielectrics, and last cases good conducting medium. Now after that we are going to learn about uniform plane waves, also called as electromagnetic waves. Firstly, how the uniform plane wave or electromagnetic wave is to be generated. Now the analysis is related to uniform plane waves which is propagating in free space. from this we are going to get the relation between electric field intensity E and the magnetic field intensity H are to be derived. Right? So before going to derive the mathematical equation for the uniform plane wave equation, let me introduce what do you mean by uniform plane wave. So according to the definition of uniform plane waves, it is defined as the wave, uniform plane wave is the wave that will have, it is the wave and that will have the variation only in the direction of the propagation and its characteristics remains constant across the planes normal to the direction of the propagation. Suppose if you consider a three-directional wave as X, Y and Z direction waves. So suppose if you are assuming electric field is in X direction and the magnetic field is in Y direction, the wave which is to be propagating in free space or conducting or dielectric should be in the direction as in the Z direction. Okay, so this is the means uniform plane waves of the waves that will have variation only in the direction of the propagation and its characteristics remains constant across the planes normal to the direction of the propagation. Means if you are assuming electric field is in X direction and magnetic field is in H direction, the wave which is to be propagating is in the Z direction itself. Means E won't vary with H, H won't vary with E, but both can vary with Z directions. That is the meaning of the uniform plane wave definition. Then we are going to learn uniform plane waves propagation in free space medium. As we know that for a free space medium, just now we have seen the three parameters which are to be considered. The propagation of the wave which is in free space medium case sigma equal to 0 and epsilon is replaced by epsilon naught and mu is replaced by mu naught. For a free space medium, epsilon r equal to 1 and mu r equal to 1, then epsilon and mu are respectively defined as with free space permittivity and free space permeability. Hence, sigma equal to 0, epsilon equal to epsilon naught and mu equal to mu naught are the three important characteristics for the uniform plane waves which is propagating in free space medium. Hence, keep in mind this sigma equal to 0, epsilon equal to epsilon naught and mu equal to mu naught for the free space medium characteristics. Now, we are going to analyze the wave which is to be propagating in free space medium, from which we are going to derive electromagnetic wave equation or uniform plane wave equation. So, uniform plane waves in free space. So, assume an electromagnetic wave traveling in free space medium. Initially, we are going to assume an electromagnetic wave which is to be traveled in free space medium. Now, based upon that, sigma equal to 0, epsilon equal to epsilon naught and mu equal to mu naught. Then consider an electric field is in X direction and a magnetic field is in the Y direction. So, just now we have seen there is an origin. If we are assuming electric field is in X direction and the magnetic field is in the H direction, based upon this, we are going to assume derive the condition to be is here. So, in order to derive the uniform plane wave equation, we need to consider two Maxwell's equations which are to be derived in the case of time varying fields or electromagnetic fields. So, there are two Maxwell's equations which are derived in the time varying fields. Those are, one is from the modification form of Ampere Circuit Law, that is from the Ampere Circuit Law, del cross H bar equal to J plus JD, and J plus JD is nothing but dou D bar by dou T, where J is said to be conduction current density and JD is given by displacement current density. So, del cross H bar equal to J plus JD we have to consider, and another Maxwell's equation which is from the Faraday's experiments, that is del cross E bar equal to minus dou B bar by dou T. Okay, so in order to derive the relation between electric field intensity and the magnetic field intensity H, then we need to consider here two Maxwell's equations which are in the time varying fields or electromagnetic fields. So one is from the Ampere Circuit Law and it is modified from the static magnetic fields, and second one is del cross E bar equal to minus dou P bar by dou T, and it is derived from the Faraday's law. So first we have considered the modified form of the Ampere Circuit Law, that is del cross H bar equal to J plus dou D bar by dou T. Now where J is given by conduction current density, and we know that the formula is J equal to sigma into E bar. So now according to the characteristics of the free space medium, we know that sigma equal to 0. Then if you substitute sigma by 0 in this equation, then J becomes 0. Hence, del cross H bar equal to J plus dou D bar by dou T. And if J equal to 0, why if J 0 means for a free space medium, conductivity value equal to 0. Hence, J becomes 0, then it is to be modified as which is equal to dou D bar by dou T. Why? Because if J 0, then the remaining term will be obtained from this equation as del cross H bar equal to dou D bar by dou T. Okay, then del cross H bar equal to, so dou D bar by dou T, where D bar is a vector, which should be expressed in terms of Cartesian coordinate system or rectangular coordinate system. Why? Because these are the three x, y, z are the three spatial coordinates which we have considered from the Cartesian or rectangular coordinate systems. Hence, the D, vector D can be defined as dx ax plus dy ay plus dz az, where dx, dy and dz are the magnitudes of the x, y, z directions and to be in electric flux densities, and ax, ay, az are the unit vectors in the respective directions as x, y, z. Right? So on the RHS part, we have here the equation as dou D bar by dou T. Now if we express in place of D bar by vector form as dx ax plus dy ay plus dz az, then the RHS part of this becomes del cross H bar equal to dou by dou T into D bar dx ax dy ay and dz az. Okay. So firstly, we have considered here Ampere Circuit Law, that is modified form of Ampere Circuit Law, which is to be obtained in the case of time varying fields as del cross H bar equal to J plus dou D bar by dou T. Then for a free space medium, if sigma equal to 0, then J becomes 0. Then if you substitute J by 0 in that equation, then del cross H bar equal to dou D bar by dou T. Now, if you want to express the D in terms of vector, let it be in the Cartesian or rectangular coordinate system, then should be written as del cross H bar equal to dou by dou T into dx ax plus dy ay plus dz az. Okay. Then, so previously we have written on the RHS part, we have the equation dou D bar by dou T, and D can be expressed in terms of vector form, means dx ax plus dy ay plus dz az. Now we are going to express on the LHS part of which is there del cross H bar. So curl of magnetic field intensity. So del cross H bar can be determined with the help of the determinant form. So here if you want to write the determinant form, suppose we have a vector called del cross A bar. We want to express this in terms of the determinant form. So first in the first column, first row, we need to write all the unit vectors as ax, ay, az, and in the second column, we are differentiating that with respect to the x, y, z, hence dou by dou x, dou by dou z, and dou by dou z. And in the third column, we need to write the magnitudes of the respective directions as ax, ay, az. So in general, the vector form is expressed, curl of a vector del cross A bar is as like this. In the first row, we have to consider all the unit vectors, and in the second row, we are going to differentiate that one with respect to the x, y, z. Then partial derivative terms we have considered in the second row, and in the third row, we will be writing here as the magnitudes of the three, ax, ay, az. So in place of here A vector, we have the field, magnetic field intensity H is there. Hence, in the first row, ax, ay, az are the three unit vectors, and dou by dou x into dou by dou y and dou by dou z. And in the third column, third row, we have considered here all the magnitudes of the three directions as hx, hy, hz. Now, upon expansion of this one, means which is equal to. So, if you expand this one in terms of the respective directions as ax, ay, az, then firstly, we are going to write with respect to x, means ax into. So, first if we consider along with the first row with the first column, then we are going to consider the determinant difference is finding here dou hz by dou y minus dou hy by dou z. Cross multiplication between these two, dou hz by dou y, dou hy by dou z. Then for the second column, we are going to write minus ay into. So second thing we are going to consider in the reverse manner, hence we have considered negative direction. Hence minus ay into minus ay means first row and the second column we are going to write. So the distance we are going to find the between dou by dou x to hz and dou by dou z to hx. Hence dou hz by dou x minus dou hx by dou z plus. And the third unit vector as az, then first row, third column we are going to consider. Now the distance we are going to write it as dou hy by dou x minus dou hx by dou y. Right? So del cross h bar equal to ax into dou hz by dou y minus dou hy by dou z minus ay into dou hz by dou x minus dou hx by dou z plus az into dou hy by dou x minus dou hx by dou y. Right? So upon expanding this one in the determinant from del cross h bar, we are going to consider some of the assumptions from the definition of uniform plane wave, which is propagating in free space medium is as h is in y direction. Initially we are assuming electric field is in x direction and magnetic field is in y direction. So depending upon this assumption, as h is in y direction, magnetic field is in y direction means it won't vary with x direction and z direction. Hence the magnitudes of the x and z directions are tending to 0. Hence as h is in y direction, hy direction only we need to consider. Hence hx, hz tending to 0. Now if you substitute in place of hx and hz by 0 in this equation, and the rest of the terms are to be as here hz, first term is 0, and here also dou hz by dou x, this also 0, dou hx by dou z, this also 0, and last term dou hx by dou y is also 0. And the rest of the two terms are to be here minus dou hy by dou z into ax plus az into dou hy by dou x into az. So these are the two terms which are to be obtained from the assumption hx, hz is equal to 0 as h is in y direction. So on the RHS part, we have expanded dou d bar by dou t as dou by dou t of dx ax, dy ay and dz az, where ax, ay, az are the three unit vectors, dx, dy, dz are the magnitudes of the d in the x, y, z directions respectively. Now, another assumption is, as initially we have considered first, h is in y direction, x and z components are tending to 0. Based upon that, we have got one of the equations like this. Now, as hy is not changing with x. Previously, as h is in y direction, it won't vary with x and z directions. Hence, we are going to consider another is one. Hy is not changing with x and it is uniform in the xy plane. Xy plane means that is equal to 0 plane. So, z direction we have considered is here propagation direction. So, h is varies with h is in y direction means hx is equal to hz is equal to 0, and as hy is not changing with h but it is changing with z. So depending upon that, dou hy by dou x, which we have got in the LHS part of that equation to be is equal to 0. Hence minus dou hy by dou x is equal to 0. Then if you substitute this term here by 0, then in the LHS part we are going to have here minus dou hy by dou z into ax equal to dou by dou t into dx ax plus dy ay plus dz az. These are all unit vectors. We need to write over bar. So dou hy by dou z is equal to ax. Now if you compare both sides unit vectors of the respective with x, y, z, then here y component and z components are not exist in the LHS part, but those two are exist in the RHS part. According to that, dy, dz terms tending to 0, and we have got only two relations as from these two. Minus dou hy by dou z into ax is equal to dou by dou t into dx ax. Okay, so both sides unit vectors gets cancelled. Then minus dou hy by dou z equal to dou dx by dou t, or dou hy by dou z is equal to minus epsilon into dou ex by dou t. Why? Because since d equal to epsilon into e, right? So if you substitute d by epsilon into e, then this equation to be written as dou hy by dou z is equal to minus epsilon into dou ex by dou t. So initially, as we are assuming h is in y direction, resultant component means as e is in x direction is to be obtained from the first Maxwell's equation we have considered is here from the Ampere's circuit law. Now in order to get another relation, we are going to use here another Maxwell's equation, which is to be in time varying fields as this one from the Faraday's law. The statement is mathematical equation is given by del cross E bar equal to minus dou B bar by dou T, where E bar is the electric field intensity vector and B bar be the magnetic flux density vector. Both are vectors only. So similarly, what we have done in the first case, how we have considered the Maxwell's equation, now how we have evaluated LHS part and RHS part. In the similar way, here also we are going to do the same. Then based upon that, E should be expressed in terms of H. Previously, we have considered H equation. From that, we have got that should be expressed in terms of E. Now, E in terms of H is going to be obtained. Then, del cross E bar equal to. So, determinant of this can be written as we have seen. So, firstly, in the first row, we have got all the unit vectors ax, ay, and az. In the second row, we need to write all the partial derivative terms with x, y, z, dou by dou x, dou by dou y, dou by dou z. And in the third column, we are going to consider all the magnitudes of the E, x, y, z. Hence, ex, ey, ez are to be written. Upon expansion, so the similar way how we have written in the previous case, here also ax into, so dou ez by dou y minus dou ey by dou z minus ay into dou ez by dou x minus dou ex by dou z plus az into dou ey by dou x minus dou ex by dou y. Right? Ax into dou ez by dou y minus dou Ey by dou z minus Ay into dou Ez by dou x minus dou Ex by dou z plus Az into dou Ey by dou x minus dou Ex by dou y. Right? So upon expansion, again we have to consider as from the definition of uniform plane wave, now as E is in x direction. So previously we have assumed as h is in y direction, now it is related to E, hence we are assuming electric field is in x direction. As E is in x direction, so Ey and Ez is equal to 0. So in that all Ez terms, Ey terms, Ez, Ey terms are tending to zeros. And the rest of the equations are to be minus dou E. So minus of minus becomes plus dou Ex by dou Z into Ay plus this is negative minus dou Ex by dou Y into Az, which is to be left out, equal to. On the RHS we have here minus dou B bar by dou T. So if you expand this one, minus dou by dou T into, similar to that of D vector, here also B should be written in terms of Cartesian coordinate as Bx Ax plus By Ay plus Bz Az. Okay, so Bx, By, Bz are the magnitudes of the B, X, Y, Z directions, and Ax, Ay, Az are the three unit vectors in the X, Y, Z directions. Right? So now minus dou by dou T into Bx Ax plus By Ay plus Bz Az. As E is in the x direction, Ey and Ez tending to 0. Similarly, Ex is not changing with y. Previously, Hy is not changing with x we have considered. Now, Ex is not changing with y. We are going to consider another assumption. And it is uniform in the xy plane. Xy plane means z equal to 0 plane. Right? As Ex is not changing with y means dou Ex by dou y is tending to 0. Right? So that equation which is to be left out is dou Ex by dou Z is equal to minus dou By by dou T. So in the previous equation, again, if this is equal to 0, only Ay component is left out. So what is there in the Ay component? Minus dou by dou T, By, Ay is left out. Now compare both sides y components, then unit vectors gets cancelled. Dou Ex by dou Z is equal to minus dou By by dou T. Or if you substitute B by B bar equal to mu into H bar, then from this dou Ex by dou Z is equal to minus dou By by dou T, which is equal to minus dou by dou T into mu into Hy, or minus mu into dou Hy by dou T. Or from this, dou Hy by dou T equal to minus 1 by mu into dou Ex by dou Z. So this is the equation which we have got from these two relations. Dou Hy by dou T equal to minus 1 by mu dou Ex by dou Z. Right? So previously we have got one of the equation as dou Hy by dou Z is equal to, that equation number 1 as dou Hy by dou Z is equal to minus epsilon into dou Ex by dou T we have got in the previous. Now this is the equation dou Hy by dou T equal to minus epsilon into dou Ex by dou T. Right? So consider this as equation number 1 and this is number 2. So this already we have evaluated from the Ampere Circuit Law. Now differentiating this equation 1 with respect to T. So if you have on the LHS part of this have your Z, and if you are differentiating this one with respect to T, hence dou by dou T of dou Hy by dou Z is equal to then minus epsilon into, already we have dou by dou t, again we are differentiating that with respect to the t, hence it becomes dou square Ex by dou t square. Consider it as equation number 3. So consider differentiating this one with respect to t. So dou by dou t of dou hy by dou z equal to minus epsilon into dou square Ex by dou t into dou t becomes dou t square. So that is the equation as your equation number 3. Now again, now to equate either of the parts, either LHS part or RHS part of that equation, now consider again equation number 2, and already it is there dou hy by dou t. Now to equate to the equation number 3, again we are going to differentiate this one with respect to z. So previously already we have z, now we have differentiating that equation with respect to t. Now in the equation number 2 already we have t, hence we are going to differentiate that one with respect to the z. So dou by dou z of dou hy by dou t. So dou by dou t of dou hy by dou t, which is equal to minus 1 by mu. Already dou by dou z is there. Again we are differentiating that equation with respect to z. Hence it becomes minus 1 by mu dou square Ex by dou z square. Right? So consider this as equation number 4. Now compare equation number 3 and 4 equations. Equation number 3 with equation number 4. So if you observe number 3 and number 4, LHS part, dou by dou t of dou hy by dou z, and in the number 4, dou by dou z of dou hy by dou t. So if you compare 3 and 4 equations, LHS part of both will be equal to same. Hence, if LHS parts of both are same means RHS parts are also same. So by comparing RHS parts, minus epsilon dou square Ex by dou t square equal to minus 1 by mu dou square Ex by dou z square. Both sides negative gets cancelled and take this epsilon into this side, then it becomes 1 by dou square Ex by dou t square equal to 1 by mu epsilon dou square Ex by dou z square. Right? So dou square Ex by dou t square equal to 1 by mu epsilon into dou square Ex by dou z square. Right? Consider this as equation number 5. Or in general we can write this equation as dou square Ex by dou t square minus 1 by mu epsilon into dou square Ex by dou z square is equal to 0. So this is the second order differential equation which is to be derived in the case of uniform plane wave or electromagnetic wave. Order of this equation to be 2. Why? Because dou square Ex by dou t square, a square 2 resembles here order of that wave equation. So in order to express that in terms of 1 by mu epsilon as wave velocity, hence we are replacing that 1 by mu epsilon with velocity v, hence that equation to be written as dou square Ex by dou t square, which is equal to 1 by mu epsilon is replaced by v square into dou square Ex by dou z square. As we know that wave velocity is given by v equal to 1 by root of mu into epsilon. Okay, as we have seen this one velocity of a free space medium, if for a free space it is replaced by 1 by root of mu naught and epsilon naught. Right? So if you substitute 1 by mu naught and epsilon naught values, then 8.854 into 10 power minus 12 into and mu naught value as 4 pi into 10 power minus 7 Henry per meter. If you simplify this equation, it is to be approximately equal to 2.99 into 10 power 8 meters per second. And it is approximately equal to 3 into 10 power 8 meters per second. So wave velocity in a free space medium is given by 3 into 10 power 8 meters per second, which is to be obtained from the characteristics of the uniform plane wave in free space medium. Right? So the wave equation is dou square Ex by dou t square equal to v square into dou square Ex by dou z square, or in general, we are going to write this as dou square Ex by dou t square minus v square into dou square Ex by dou z square is equal to 0. This is the simple uniform plane wave equation or time varying field electromagnetic wave equation is the order of the second, right? So the rest of the parameters and how the wave is to be vary. What do you mean by alpha, beta and gamma? Attenuation constant and phase constant and propagation constants of a plane wave. Then based upon that, one more term called intrinsic impedance. How these are to be vary, we'll continue in the next. So in this lecture, what we have learned is introduction to wave characteristics, electromagnetic wave characteristics. Under that, we have learned what do you mean by wave, different examples for the wave, and what carries the wave, and followed by definition of a uniform plane wave. Then we have seen or we have derived the mathematical equation for the electromagnetic wave equation or uniform plane wave equation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.